Thank you very much. Hello everyone, I'm Kubi, and I want to start with the fact that this is my first ever conference talk, so I'm super excited. ChatGPT told me that I shouldn't say I am worried or anxious, I should say I am excited. No, it doesn't help. And my wife is also watching me. She said I support you, but it also doesn't help. But I love you, honey. Hello. My in-laws are also watching me, but yeah, don't ask me how this has happened. All right. So, bit about myself. I'm Kubi, or Kubilay. I'm a software consultant at Xebia. I'm actually a colleague of Urs. At Xebia, we help our clients to build amazing applications. So that's what we are trying to do there. And when I do that, I mostly use Kotlin, Java, and Go. As you can imagine, I'm a backend developer. And I'm also a Kotlin trainer. So it's a picture of me from one of the Kotlin trainings. And while building these amazing applications, we use many tools, languages, frameworks, right? And there is one thing I expect from these tools is that I want them to write things easier for me. So what I mean by that, in certain situations, there are some good practices to follow, right? We all know those. This is why we are here to learn about this. So what I expect from a tool that to make these good practices easier so that it's naturally followed by the developers. So there is less friction. So we end up in a better product. I also expect these tools to make wrong things harder. So put friction so that the developers are prevented nicely from doing the wrong things. And talking about making the right things easier, Kotlin is one of the greatest examples comes to my mind because it has so many functionalities that makes these correct things easier for us. And a very small example is immutability. We like it, right? In many places, immutability makes our code much, much more maintainable. And therefore, I expect it to be easier in the language I use. And how Kotlin does it, for example, lists are immutable by default. Yes, you can create immutable lists in many languages, but if I know that in the majority of the cases the immutability is the desired state, then the language should make it default. And I have the keyword for immutable variables as well. Yes, in the Java you can also use final keyword, but why there's an extra friction to use the immutability if it should be the default case in most situations? And there is another programming paradigm I will talk about today, which is called asynchronous programming. In some certain cases, it is a really, really helpful thing. So in this talk, first I will explain what are those cases the asynchronous programming addresses. Because we know that in software development, there's never a single good thing. It always depends on the situation. So I will explain in which situations the asynchronous programming is good. And then I will briefly explain how Kotlin makes asynchronous programming easier with the coroutines and suspend functions. And while I'm on this stage, this is for me the most exciting part, is that I want to show you how coroutines and the suspend functions works under the hood. So let's do a bit of a show of hands to see where do we stand. So who has worked with Kotlin? All right, this was already asked in the morning, so all right, we have more or less the same audience, that's good. So who has worked with any kind of asynchronous or reactive libraries? That's great, that's great. What about coroutines and suspend functions? Yes, that's good, that's good. So, first, which problem asynchronous programming addresses? In order to understand that, we first have to look at the synchronous programming. So here, this will be the example I will use throughout this presentation. It's a very simple example. I have two functions, get product and product sales, which gets some data from some external services, and I have a get product function that combines this information and creates a product report out of it. And what I'm looking is our usual synchronous code, right? It's what we are very much used to. And these two operations, we will call them as blocking I/O operations. So what I mean by that, I/O means input and output. So it could be anything like a database call or fetching a data from external service. And what I mean by blocking, we will go into details with this, but for now, as a summary, blocking I/O means that when I'm doing these I/O operations, I'm actually just waiting for a result from an external service, but my system, my threads are still blocked. So this is what I mean by blocked I/O operations. And if I want to create a REST service out of this with Spring, let's say, it's pretty easy, right? I just create a controller, put this function there, and then I have a REST endpoint that creates a product report. So in which cases this structure could struggle? For that, let's look very briefly how a REST application works in a synchronous architecture. In this architecture, I have a thread pool which has a fixed number of threads. And whenever I get a request, a REST request, one of these threads assigned to this request to execute the operation. And when it hits an I/O boundary, when it's making an I/O operation, there is nothing else to do for that thread but wait for the response. So that's what we meant by blocking. So it blocks the thread while waiting for I/O operation. So what happens if I get another request, I basically assign another thread from my pool. And it also hits some I/O boundary at some point, and it's also blocked there. And this goes on for multiple requests. But at some point, my thread pool is empty. So what happens? Nice landing. So what happens if I get an extra request? No more threads available, so I cannot process this request. So that's the problem. And you might think that, hey, but you can add more threads to thread pool. Why you don't do that? Luckily, I have this slide. Because threads are expensive. And these are not AI generated. I put the emojis by myself, right? Because they take up memory space. So this is important. It's usually 1 megabyte per thread, but it depends on the operation system and certain factors. But it takes a good amount of memory, so you are limited in terms of memory. But even if you are not limited with the memory, it's also expensive to switch between threads. So after some number of threads, your CPU is actually spending more time switching between threads than actually processing the requests. So this is why we can only have some amount of threads, and after that, it's just not effective. But you might think that, hey, this is what most applications looks like. That's just usual synchronous applications, and that's true. It doesn't mean that it's a bad thing or it's always worse, but in some certain situations, it hits a limit. And what is this? It basically happens when two conditions happen at the same time. First, you have high number of requests coming in your application concurrently. So this is what we call high throughput. And you also have long I/O operations. This could mean that just making calls to external services, for example. And one example could be a service that aggregates data from different services and returns it back, and it gets a lot of user requests. So when these two things happen, then our threads are not enough anymore. Our thread pool is exhausted because we have limited number of threads, and they are in waiting state. Then, as a consequence, our application becomes unresponsive under the high throughput. Can I have one of these? This day will be useful. So this is how I can summarize it for the synchronous programming. Yes, it is simple. It's what we are used to, but it really suffers under the high throughput situations. So this is what where asynchronous programming comes into picture. So asynchronous programming is not a specific way of doing things. It's actually a general programming paradigm, and there are multiple ways of doing it. What I aim in all of these approaches is same though. I don't want to block my threads during the I/O operations. So that's what all I am trying to do. And one of the main approaches here is the use callbacks. So when I have callbacks, I simply add a callback function to my function signature as a last parameter. So this means that instead of waiting for get product or product sales to be finished, their execution is immediately executed and returned, and the rest of the operations I do, they are in the callback. So when I call the get product report, it will very quickly finish because it's not waiting for I/O operations, and the rest of the operations will be handled in the callbacks. So this could be familiar to folks from JavaScript background or who has worked with JavaScript at somewhere in their career. But the problem with that is it's complex. It's really complex. And it has even a name, like callback hell, because after some point you have so many callbacks and it's so hard to read your code. It's so nested. And how would you even connect this with a controller? Like imagine the get product report, how would you put it in a controller? Maybe you can find a way, but there's no an easy way to do it, because this approach is not something very common in the JVM world. Idea is solid, but it's not common, and it's complex. So putting in this table, what I have now, yes, now I can have high throughput in my application because I'm not blocking the threads, but I lose a lot of simplicity. So that's the problem. Before moving further, I want to briefly explain this concept called event loops, because for synchronous programming, I showed you how our REST application handles one thread per one request. But what about asynchronous applications? So most of these asynchronous approaches use event loops or a tool, a system similar to that. In an event loop architecture, when I have a request, I put it in an event queue. And then there is this event loop in the middle of everything. And this time, it doesn't have a large thread of pulls, but it's a very small pool of threads. It's usually amount of the CPU cores, or maybe even one CPU in the JavaScript, one thread in JavaScript, for example. And then this event loop takes the request, process it, and when it hits an I/O, it registers a callback, and then frees up the thread. So that's the crucial part. When I hit an I/O boundary, I register a callback. Oh, where's my callback? I register a callback, and I free up the thread. Sorry, let's move from here. I register a callback, and I free up my thread. And that callback is somewhere else, waiting for I/O operation to be finished. I get another request, it's put it in the event queue. I get another one, it's put in the event queue. And what happens then when one of these async operations completed, then my callback will be initiated, it will be put on one of these threads, the result will be executed, and thread will be freed up again. Same thing for the other callbacks. So that's the whole idea. Even though I have a very small amount of threads in my thread pool, since I only use them for non-I/O operations, since they are never blocked, it's always enough to process large amount of requests. So this way, this is how I can process more requests with the same hardware resources. So almost all of the approaches we will talk here use a similar approach like this. And the crucial thing is that we never block the threads with I/O operations. Ooh. And the next approach, which is something you might be more familiar, so all these examples are Kotlin examples. but you might be seeing this more in the Java, is the reactive programming. And in reactive programming, what you see is gone, is callbacks. Oh, thank God. So that's good. But I have this now, mono. And what is a mono? It's either a feature and promise. Apparently, three, four names for features were not enough. Now we have another name, mono. All right. So mono is basically a feature, and what a feature means that it is a return value which will be available sometime in the future. So that's it. That's the promise. Also, same thing. So when get product is executed, it will almost immediately return a mono, but it's still waiting for a sync operation to be completed. It doesn't have that value yet, but it will have sometime in the future. So this is how I structure my application with mono types. An important thing here is that these two operations, of course, should be non-blocking, because we have seen that in the architecture that runs this system, we have a very small amount of threads. And if somehow I let a blocking operation to go there, these threads will be blocked, and everything could come to an halt. So I have to be careful that if I'm using a reactive programming, I should use non-blocking I/O libraries. So this might be already better than callbacks. Yes, my function signature is a bit better now. I don't have callback hell. But still, my application code is invested with all this logic. And it's like, why is that? I want to do one simple thing, but why is now suddenly my application code has to include some stuff about how I execute the I/O operations? So it doesn't make sense a lot. Though, as I said, this is a common thing used in the JVM world. For example, if you use Spring Web Flux, it's a reactive version of the normal Spring Boot, and then you can just return a mono from your controllers, and you have a full reactive stack. And of course, Spring Web Flux and Spring Stack also includes reactive libraries for REST clients and databases and everything. So you can have the full stack. So again, comparing them in this table, it's like we still have the high throughput. This is great. More requests handled by the same amount of hardware, but we're still lacking the simplicity. So that's bad. This is always a choice has to be made by the teams. Should we go for high throughput and risk for the high complexity, or vice versa? The question is, could there be something better? And yes, so this is where Kotlin Coroutines comes in with the suspend functions. And in the next chapter, I want to explain how this is made easier by Kotlin. So this is what I mentioned way in the beginning, right? If this is something good, if I want my teams to use this, if I need this really, and then I expect the tools, the languages, the frameworks I use to make it easier for me, not complex. So this is how same example would look like with the Kotlin coroutines. I can imagine this is not a very big surprise for most of you, which is great. And for the rest, you might even think that, hey, you are showing the same example. Maybe this is wrong slide. But yeah, it's the same example. The only thing extra here is the suspend keyword. So that's the key thing. That's how Kotlin makes it easier. All you have to do is write your code in a normal sequential way you're writing, and just make your function suspend, and then the Kotlin will make sure that this will run in an asynchronous manner. But of course, that's not the only thing you have to do. You still have to make sure that you use non-blocking libraries in get product and get product sales. Of course, you still have to use some sort of a asynchronous web framework, which could be again Spring Web Flux, because it supports the coroutines with the asynchronous stack. So this is great. But I still want to briefly explain a bit what are the Kotlin coroutines. I think this is important also for the rest of the slides. So first, let's talk about the JVM's own threads. So JVM's own threads, as we call them platform threads, they're unit of execution for concurrent operations. But the problem with them is they are one-to-one tied with the kernel threads. This is what makes them expensive. This is what makes them hard to context switch and everything. What Kotlin introduces here is coroutines, which are basically lightweight threads. And they take less amount of memory. It's easier to do context switching. So you can have much more coroutines in the same hardware than you can have JVM threads. And still, they run on this JVM and platform threads, because that's it, like you're in a still JVM environment and you have to use the platform threads. Of course, Project Loom might introduce something different here, but let's keep that on hold for now. And the core thing is that they can be suspended. So when a coroutine is suspended, it will be taken out of the platform thread. So that's what makes them special. So they don't keep the platform threads busy while in the blocked state or waiting state. So that's the crucial thing. And when they're suspended, they don't block any other threads. So summarizing once more again, like what we see here is that coroutines, yes, high throughput is still there, but the simplicity is now greatly improved. And for me, this is what happens when something is supported on the language level. Something was considered on the design phase. It's not on the framework or library level, it's on the language level. It's designed for that. The simplicity was one of the goals, and it's achieved. So it's a really nice sweet spot where you get both simplicity and the high throughput. All right, but we are here to see how Kotlin coroutines works under the hood. And at this point, I think we are all sure that my wife is stopped watching, so I can be a bit more relaxed. So here I have the same example. Only thing I did is I added a main function so that we have a full code stack here. And if you have noticed, main is also marked as suspend. This is something you can do. You can just mark your main method as suspend, and it will work in a suspended manner. And you all know that you can only call suspend functions from other suspend functions. This is why my main function has to be a suspend function. So this will be the example I will be using. And before going all these slides and everything, let's use something and let's look briefly what's actually under the hood, because IntelliJ actually gives me a quite nice tool. Oops, sorry. Right, so you can see it. Is it visible enough? Great, nodding heads. So I have the same example here. Main function, get product report, get product and product sales. These are kind of a mock implementations, not very much important. So what I will do here is that this is the Kotlin code, right? I will come here, tools, Kotlin, show Kotlin bytecode. And of course, I don't expect you to read this. You're not an oracle, but you can click the decompile, and voila, what I will see is that it's the decompiled Java code out of this. Whoever used this before? Nice, it's great. I really like it. So you don't have to check some book or library or something. You can just look it by yourself. So let's have a brief look. What I want to check first is my get product function. So there is a lot of stuff going on there, so we need some scrolling here. So here I will notice a couple of things. First, for some reason, my return type has changed the object. All right, one, let's keep that. Second, there is something called continuation added here. All right, this two. And there's a lot of going on with my function body, but that's fine. Come on. So this is basically what I saw in the decompiled code. So I saw my main function and all other functions, they all added with an extra parameter called continuation. Their return type has changed to object, what I'm doing right now, I'm showing you a kind of a beautified and Kotlinized version of it. And the return type is any here, and it's the object in the Java. And for the rest of the slides, anytime you see a dotted lines, then it means it's a decompiled code. But I made it a bit nicer so we can understand, and I made it a bit more in the Kotlin syntax, so it's easier for us to compare. So these are the functions I have seen, and I will try to see how they are implemented and generated by the Kotlin. And let's look at this continuation part first, right? It's one of these three things that I see changed in my function when it's transferred into Java code. And if I look at it, let's put the context aside for a second, because I want to focus on resume it. It might look familiar to you from previous slides. This is neat. It's actually just a callback. Continuation is a callback interface that will be executed when a sync operation has completed with a return type, with a return value. And it has these helper functions in the Kotlin, so it can handle the resume with a normal value, also resume with an exception. So both cases are covered, and it has this result type. Result is basically just a wrapper around a single value that can mark success or failure. We also seen in one of the previous presentations. Going back to my example, so this was my decompiled code. And this was the function signature from the earlier slides from the callback. So the top one is the decompiled suspend function, and the bottom one is the callback. And you can see that, yeah, again, they're both callbacks, right? So in the end, they all goes back to the same concept. But what is different is that bottom code is something I write by myself. It's an application code. I have to write those callbacks. I have to manage them. But the top one is a generated one. That complexity is abstracted away for me. But because we are curious people, today we want to see a little bit about this complexity. We want to see behind this abstraction. All right. So when we talk about suspend functions, it's important to know that, okay, what do we mean by suspending? So when a suspend function means that it can suspend execution of a coroutine. But if a coroutine is suspended, what happens to function? Function also has to be suspended. And when a suspend function can suspend a coroutine, is that it can only happen when a call to another suspend function is happening. So the suspension happens at random points. It only happens when a call to another suspension function occurs. So this whole thing, suspensions, continuation, could be a bit complex. So I want to show it with a diagram. So when I first start, I put this coroutine machinery. It's basically dispatchers, this event loop, and everything is a bit hiding the complexity around, because I want to focus on my main call stack. So when my first application runs, the coroutine machinery initiates my main function, and it has to be run from somewhere else because it also needs a continuation itself. It runs my get product, and it runs my get product report, then it runs get product, but the get product has an I/O operation, right? So it hits an I/O boundary. So what it does now, it suspends the execution of coroutine, and it sends this signal up. And what get product does, it also does the same thing. It also propagates this signal up the call chain all the way to the coroutine machinery. So what happens now, coroutine machinery suspends the execution of coroutine, registers a callback to resume execution of this coroutine when the result is ready. So this is the first call stack. In our application, I had 2 suspension points, right? Because I had 2 suspension function calls. So when a result is ready from the get product, now I will have another call chain because the result is ready now. So coroutine machinery says to get product, hey, you know what? This IO response you are waiting is ready. So callback is executed. It resumes this get product. Remember the function signature from the continuation. And the get product resumes to get product report. But get product report has to do some other stuff to do. So it goes to get product sales. This time get product sales hits an IO boundary and it suspends the get product report function. And it's propagated all the way up, and the coroutine is suspended a second time. And the third time, when the result from get product sales is ready, it's resumed from coroutine machinery. Then it resumes back to get product report. Get product report sees that, okay, I'm done. I don't need any other suspend functions. It resumes the main. Main also does the same thing. And it resumes the coroutine machinery. And coroutine machinery understands that, okay, this full cycle is completed. This coroutine is actually finalized now. So because that's the same coroutine. It did a full circle. It's suspended twice, but then it's now finished. And the cool thing is that in these 3 different executions, this coroutine could have been executed on different threads, because that's the whole idea. When it's not executed, when it's suspended, it doesn't block any thread. So this is the part about how this call chain looks like, but now we might want to see some code. Before that, let's quickly summarize. Suspend functions can suspend coroutine execution. Suspension happens at calls at 2 other suspend functions. Suspend functions are paused while coroutines are suspended. We will see how this happens. And continuation that resume it is used to resume suspend function when async result is ready. So this is what we call as callbacks. So the question is, JVM doesn't have any notion of suspend functions, right? JVM doesn't have any notion of pausing functions. So how this could be done? How Kotlin compiler transforms our suspend functions into regular Java functions that could be executed and paused and resumed. Because this is what we have seen, right? It's the function is paused twice and then resumed twice. So how this could happen? Again, just reminding our example, but here I will be mostly focusing on the get product part. Other parts would look similar, but it's better for us to just focus on one part. So the question is how this can be paused and resumed. I know that it has 2 suspension points, so it means that my function will be paused and resumed at this point. And it also means that these 2 suspension points actually splits my function into 3 different executable blocks. So that's important, 3 different executable blocks. And I will call them as label 0, label 1, and label 2. From now on, I'm going into this decompiled word. What we will do together is that we will come from here, a regular function, into this transformed function we have seen in the IntelliJ. But be aware that we are not creating this solution by ourselves. This is already implemented by Kotlin, and this is already done by Kotlin transformer compiler. We are just building line by line what they have already done. So let's first divide our code into these 3 chunks and control it with our label with a when statement. So now I have 3 different scopes divided by 2 suspension points. But where this label comes from, it actually comes from the continuation. So continuation actually also stores my execution state. So it's a callback, but it is also something that stores the state of my function, so it can be resumed. Here it calls this label. With the label, I control which block I'm executing next, and whenever I execute a block, I update this label. So next time, it goes on from the next block. And this part is important, that every suspend function wraps the continuation coming from its own parent with its own continuation. So that's really important, and we will see how this comes into effect. And then, of course, this wrapped continuation also passed to my children. This is what I need, right? I have this callback chain. I have to keep this connection from top to the bottom. This is why I also pass it to my children, but only to suspend functions. So in order to visualize this wrapping a little bit, this is the call chain of the first branch of my function. So when it starts, coroutine machinery has this kind of an initial continuation. It's passed to main function. Main wraps it with its own main continuation, pass it to get product report. Get product reports wraps it with its own continuation, and then it's passed to get product, and get product also calls someone, right? So it also wraps it with its own continuation. So that's the key idea. I keep wrapping the continuation, so every function somehow stores its own state on the same continuation. So that's a very key detail here. So I'm not creating a new continuation, I'm wrapping it with every function pass. So every function can store its own state. But this callback chain is keep intact because it's still the same continuation. Going back to my example, I'm still building it up, and you might also see that I'm doing this wrapping operation only once, because this function will be called actually 3 times. Once for initial call, and 2 others after the suspensions are resumed. So this is why I have to do it only once. I shouldn't wrap it 3 times. And every time this function is executed, a different block will be executed, right? And then it also means that I cannot pass values from one block to other. And get product and get product sales, they are suspended functions. Their results are not ready anyway, so I cannot do this while product equals get product, because it's a suspend function, its result is not ready yet. This is why results from the previous suspend functions pass to next block via continuation. So continuation always holds the result of previous suspend call. This is what you see here. So the result of get product is transferred to label 1 via continuation.result. It's the same thing for the product sales. Also, some intermediate values, not the return types from not always the return times from suspend functions, but any intermediate value that I have to pass between blocks, it also has to be stored on continuation. Because again, these blocks will be executed in different times. They cannot reach the variables from each other. And failure cases will be handled as well, because result is a result type, as we have seen in the continuation interface. But here I convert it to an exception. So this is the important part. Like I said, this function will be executed 3 times, right? And the first time it hits the get product, but it suspends. This is why I first return a coroutine suspend. Also the same thing with the label 1. It calls the get product sales. It also suspends. This is why I also return a coroutine suspended call. So in first case, in first two executions, my function returns a suspension signal up to the call stack. And if you look at this, it's just a enum from the library, so it's not something very special. It's just an enum that is propagated all the way up, so everyone in the chain, also the coroutine machinery, knows that there's a suspension going on. And this is why my return type has actually been changed to any, because now it can either return the result or it can return the coroutine suspended signal. And as you can see in the label 2, when all suspensions are completed, I can actually return the result, but not in the first 2 executions, because they are suspended. I have to return a suspend signal. And Kotlin is smart, so this is what we like it, right? It makes things easier. Sometimes suspend functions doesn't have to really suspend the coroutines. They can just return the results. That's possible. This is what this optimization does. So it checks if I really get a suspended signal back from the getProduct suspend function. If I did, I really suspend it. But if I didn't, I just get the result and move it to the next block, and the next block will be executed immediately, because otherwise coroutine will be suspended, it will be put back. It's unnecessary, so this makes a great optimization. So that's actually how the Kotlin compiler transforms a suspend function into a regular Java function that in this case will be executed 3 times, but every time one block will be executed with the continuation storing the values from the previous suspend execution and also the previous block. So we have seen the suspend part. We haven't seen yet the continuation, what's going in the continuation, because I show you the resume it, but here you don't see any resume it. You might think that, okay, why did you show me that then? The brief summary: Kotlin compiler transforms suspend functions into regular Java functions that can be paused. These functions split in the blocks, separated by labels. These are called multiple times, and they store their state in the continuation. So the final part in the puzzle is that how this continuation interface is implemented for suspend functions by Kotlin. Because I just show you an interface, but I didn't show you any implementation. So this was the interface we have seen. I'm only interested in the resume with. So my child functions, the child suspend functions I call, will use the resume with from the continuation I pass them to resume the execution when they are completed. So this is what I am implementing. Let's remember this picture. Here I'm interested in the getProduct report. So I will look at the getProduct report continuation and its resume with function. But again, remember that its resume with will be called by its children, either from getProduct or getProduct sales. Again, this is the reminder from the previous part. This was the suspend function implementation, and we have seen getProduct continuation. We haven't seen insight. We will try to see insight right now. So let's look first what should go inside the constructor, what I need to construct that. First, my parent, right? I'm creating a callback chain, so I need the continuation from my parent. And the second, I need whatever variables were in the suspend function's method signature, because these will be required to call my function again, because my function again will be called 3 times. And in the last 2 times, it's calling from children, and they don't know my parameters. This is why it's there. Oh, sorry. Then I'm going with the methods. I have the resume with method. Then I'm going with the class variable. So what I have to store in the continuation. These 2 are the essentials, label and the result. Label holds where I am, and the result is the result from previous suspend function. And I have to put any intermediate variables specific to my own continuation. Now I finished the class definition. I can go on the function definition. What I want to do first, I get the result from my children. I have to put it in the continuation so that my function itself can get the result. And the next thing, I have to call the function itself, right? That's the whole thing. My child has finished its job. I have to call myself. This looks a bit interesting, but that's the whole callback idea, right? This is what I'm doing with the callbacks, and this function is smart enough to know where it will be continued. It will not start from scratch, because I'm passing the continuation as this, and this continuation has an updated label. So it will only continue from where it's left off. And of course, it could be also suspend, and in this case, it will just return, because there's nothing else to do. My own function can also suspend. Okay, my child doesn't have to do anything with that. But if it's not suspended, if I'm not suspending myself, now it's time for myself to call my parent with the resume with to continue the callback chain. And exceptions are also handled. And voila, this is my continuation. This is how a callback is basically implemented by Kotlin. I'm right now out of time, so I will skip this slide, and I will do my conclusion. So the thing is that what we have seen in the beginning, asynchronous programming increases throughput on the services with high load and long-running I/O operations. So that's why I wanted to use it. And then we've seen that how Kotlin Coroutines combines the simplicity of the sequential programming with the performance of asynchronous programming, and then how Kotlin use suspend functions for asynchronous operations, which are in fact just callbacks. And what I would like to summarize it in one sentence is that simplicity of coroutines, for me, comes from the language support for this async programming paradigm with the suspend functions. They are nicely abstracted from us, so our code stays simple, but as you have seen in the last example, they still have great engineering inside. So, thank you very much.
Thank you so much, Kubi.
Yeah.
I think giving the first ever conference talk as the last speaker of the day is not an easy setup, but you've done super well.
Thank you very much.
Yeah, it was a really nice close.